going to. All right. Good evening once again for those that have just joined us. I send apologies from RSA team for yesterday's session. Yeah, we happened to have gotten an emergency towards 8, so we apologize for yesterday's session. And it's a pleasure to have you. I understand you are notified that today we shall have a session, and you're most welcome. I hope I'm audible. If you don't mind, you can type 1. I hope. All right. Thank you so much, Engineer Titus Jeremiah. All right. Yeah. So today we are going to dive into foundation design. Maybe just to give you a small background, whatever we have done, whatever we have designed, the various roads that we specified for the structure, they are not going to end at the slabs or the beams or the columns. They have to be transferred to the foundation. This is something that is so critical when it comes to structures, because you might have perfect slabs, perfect beams, perfect columns, and everything is working your way, but all of a sudden, a failure starts from the foundation. You find excessive settlement at a given footing or foundation that probably was not anticipated during the geotechnical investigations. So you might have a settlement. Usually it's, if at all, it's the structure is settling throughout at the same level, it is okay. But what is most dangerous is the differential settlement. You find, for example, a given footing is okay, and you find some other footings at different locations that are settling way greater than what was anticipated. So, of course, the structure will mobilize to resist whatever stress. It will still act as one structure, but in the event that the settlement just continues and can't be counterbalanced, then you might have failure starting from your foundation. You have seen floods wash away things and the foundations remain protruding on the surface, but the structure is still standing. Yeah, so our foundations are critical when it comes to structures, because they are the members that are going to transfer whatever loads we've applied onto the structure, right from your topmost story. All those loads will be transferred to whatever foundation system that you have underneath. So allow me share my screen. Oh. All right, I hope my screen is still visible. You can just type 1 if you can see the robot software open. All right. Thank you so much. I think it's a culture at RoadSub. I shouldn't just continue minus hearing probably from one or two participants. Just unmute and let us know how your day was. Then two representatives, just two people, then we proceed. Just two people can unmute and say hello to us, or I can choose randomly.
Hello everyone.
Yes, Ingenia, hello.
How are you? My name is Shonai Mashamba. How was everyone's day? Mine was fine. I'm a bit behind in terms of the training, but I'm trying to make follow-ups. Though I'm facing one or two challenges, but I think I'll wait for the day that we are going to have the feedback session. Yeah, thank you.
All right, Ingenia, thank you so much. Yes, it's still great that you're facing challenges, because in engineering, once you face challenges, that is when you're forced to think probably outside the box, and that is when you get the concept even much better. Otherwise, if at all you're not finding any challenge, then you might have probably, maybe you're far ahead of us, or yeah, but it's a pleasure, engineer. Someone else?
Yeah, good evening, Captain.
Good evening, engineer.
Yeah, how are you doing?
I'm great.
Yeah, yesterday we were unable to have our session yesterday, but I asked Deogratius some question yesterday because I feel like when we enter the design aspect of this milestone, like for the beams, especially for the beams, I keep asking this question. Maybe you don't get my question. You haven't shown us the worst case scenario load that is acting on the beam. If you are to design manually, you have to see that load that's come from the analysis, then you will now use it for the design. But now you are only showing us the NZ, the forces and the moment acting in the X, Y, and Z direction. Whereas the load of PZ, though if you click on the option button at the down where we normally on the section shapes and all, we have a place that shows load description. But in that load descriptions, like if you look at the longest beam, yes, that is of the same yes, the longest beam, there is a place that we have a point load. But if you use the diagram in the result, we have a place that we have the map and the diagram. If you view it from the diagram, then you now turn on the load description. It's not showing us the point load. Whereas we have the UDL and we have the point load acting on the beam. From the secondary beam, there is a load that will be transferred to the primary beam. So I don't know if you understand my question. Been battling with that, so I want to understand that place better. So a beam cannot be completely uniformly distributed load. If there is a point load, there is supposed to be an imposed load on the beam towards the span of that beam. So please, thank you.
Yes, engineer, I've understood your question. I will demonstrate that how robot visualizes point loads that come from secondary beams. I will
Hello.
Hello, engineer. Yes, I was explaining towards the end, I'm going to demonstrate how robot visualizes point loads. Worry not, I will tackle it towards the end.
No problem. This is another speaker speaking.
Oh,
Yes,
right.
this is Philip. I don't want to appear like I'm answering the previous question, but from what I understood is that you see you cannot see the point load because what you are visualizing are the internal forces after analysis. So, or maybe to see the PZ might be a bit challenging after analysis, but you'll see the effects of that point load. I think that's how I answered myself, but I'm eager to wait for your conclusive response on that. Now, my next question was about load combinations. You see, in construction, for instance, if you've designed a building that has a water tank at the top, at the rooftop. So when putting in the load, you consider that the water tank will have water, isn't it? So you consider it with the load, with the tank full of water. But again, there's a scenario where the tank will be empty. So how do you consider that scenario during analysis? Is there a way that you can introduce a load combination to affect that scenario, or how will you deal with that situation? Thank you.
Yes, engineer. So I will. Sorry about that. So yes, actually, engineer Philip tried to answer the beam part. Yeah, but I will still demonstrate. When you import a beam into the design template, whatever spans it has, whatever secondary beams are attached, they will be imported. But what robot demonstrates is that at this point, there is a beam attached, but it does not show you the point load from the beam, but I will demonstrate that. Going on to your question, for example, if at all you have a water tank on top, and it will be at some point it will have it will be full to capacity, so it will carry a certain load that probably would be the worst case scenario. And the assumption is if your structure can stand for the worst case scenario, then what will happen when your water tank is empty, meaning the load will be something that is very small. If you had maybe a 20 kilonewtons per meter squared when it was full, and when it is empty, it has a 1.5 kilonewton per meter squared, meaning your structure will be carrying something that is very small. So if you design that specific slab to carry the load of your tank when it was full, probably this is just an assumption that it was maybe 20 kilonewtons per meter squared, and the slab can withstand that, then it will withstand when it is carrying probably an empty tank that is only accommodating self-weight. So if your slab passes for the worst case scenario, then it will stand in whatever, if at all the tank is halfway or empty. So when it is empty, meaning it will only be its weight that will be acting, that just the self-weight. So that is the only assumption, that if at all in my load combination I capture the worst case scenario and the structure stands, it will stand forever, even if the tank is empty or halfway or a quarter. That is the assumption. All right, so let me dive into what we have for today. All right, I'm going to go to the geometry. So I'm just going back to where we all start from. I'm going to just exit these. These are other views so that I remain with the default plan and the view, which is the 3D. So foundations. As I highlighted earlier, maybe for those that have just joined us, foundations are critical. You might have a structure that is perfect. All elements are functioning properly, but if at all you didn't carry out very good geotechnical investigations, you might end up encountering probably soils that will undergo swelling, or that have that will create differential settlement. If at all the structure is settling as all points settling at the same rate, that is okay. You will not have differential settlement. The only question would be how much will it settle? Otherwise, it might settle and you find doors turning into windows. But yeah, if at all it is settling at once, then that is okay, because then there are no other stresses, but still it shouldn't settle so much beyond what was anticipated. If at all, for example, this portion settles more than, if at all this point settles more than this other one, then you have differential settlement, meaning you're introducing other secondary stresses that are meant to be resisted. But still, if at all the settlement is not that much, the structure will handle. So all the loads that have been applied on the structure have to be transferred. And how are they transferred? They are transferred through columns. For example, this column I've highlighted, it goes all the way until when it gets in contact with the soil type, whatever soil type you have at the base. So all the loads will be transferred up to the base and dissipated to the soil. If the soil can handle that bearing capacity, if at all the bearing capacity of the soil can handle the loads, then you will not have settlement. If at all the loads are way greater than what the soil can handle, then it will settle or it will deform so that it mobilizes more stress to counterbalance whatever force that is applied. As you know that when you apply a force onto an object, there is another force in the same direction, in the opposite direction. So if at all we apply stresses at this point, if it is more than the bearing capacity of the soil will deform, but in deforming, it will mobilize more stress, but that deformation should not be greater than what you anticipated. Foundations are divided into very many types: deep foundations, shallow foundations. Deep, those ones would be the piles, and as you're aware, they can be end-bearing piles or friction piles, depending on the load transfer mechanism. End-bearing, they transfer it to a firm strata. Friction piles, they utilize the friction resistance on the sides to counterbalance whatever forces are applied. So what we are going to deal with are the shallow foundations, the pad, the raft, the strip, meaning they're going to dissipate loads at a shallow depth. So we have a very good firm strata probably at a small depth. So I'm going to go to the front. Let me just use this tube. So our main interest now when we are dealing with foundations is the point of contact. This the point at which the column is attached to the soil. Now, the same applies to all design procedures. We need to extract whatever elements we are going to design and extract them into a more organized model where we don't have all elements visible. So, but now when it comes to foundations, I'm going to highlight starting from my right to left, but now my emphasis is going to be the rectangle that I'm going to use to highlight. It should be enclosing this point, the node at which the column is attached to that pin or to the soil, because literally this is where our soil is. So I'm going to highlight from right to left, but I'm going to pay much emphasis so that the rectangle highlights, you can see the rectangle is enclosing the nodes. So our interest is more on the nodes. So I'm going to extract this the normal way. After highlighting, you come here and edit in new window. So I'm going to extract them into a new window. So in this window, I will have only the columns and the nodes. Because I know when I was highlighting, I highlighted the nodes. The same applies to all design procedures. Once I'm to design, I need to look at the results. If I'm to look at the results at these points, remember our emphasis is at the different nodes. That is where our emphasis is. So as you can see, my model has results available. So I'm going to go to results and go to diagram of members. It's almost the same procedures, but again, you will see when we go to design, they are the same procedures, but for different elements. So now, as I said, our emphasis is at this node, the node at which the column is attached to the soil. To visualize the results, so now I'm going to focus, to put my focus on the reactions, because I need the reaction at that point. So I will choose reactions, and then the reactions are in the global axis. So if I want the FZ, it will be the one in the Z. So I'm going to toggle on the FZ so that I have reactions in the FZ, the global axis, and then turn on the description. Then apply. As it has always been the norm, because you have this other side of parameters, you have the minimum will be in a light green, then the maximum will be in red. The same applies to when we sorted beams. Whatever moment we wanted to design for, the maximum was in red and the minimum was in green. And I'll keep probably answering some few questions as I proceed. When I realize probably I could hint on something. So we have the red that is showing you the maximum FZ, and green showing you the minimum FZ. So you can see there is a column here. So all you have to do to organize, you just have to zoom in, then click on normalize so that you have them closer to, so you can know which column. For example, this column has the maximum FZ, and the minimum is along the wall. So remember, we have different nodes. So there is a node along this wall that has the minimum FZ. We are looking at FZ because all the loads are going to be transferred via this global into the soil. So I'm going to just, currently we are in self-weight, I'm going to just turn on combinations so that it can now capture the maximum FZ for the different combinations. As you can see, the one that has the maximum, the minimum is somewhere else, as along the wall. There is a node along the wall that has the minimum. So this is the FZ. So this column, among all columns, this column has the maximum FZ of 30,000 something. When you check others are in 10,000, and as Engineer Gatimo mentioned, so here the same applies to the way you grouped columns. We can be able to group our foundations depending on the maximum FZ or the range of the FZ. So if this is in 3,000, maybe we could say 3,000 and above, whatever column has 3,000 and above, that will be our column 1. Then whatever has maybe 1,000 or whatever has 1,500 to, or we can set 2,000 to 3,000, that will be our column 2. Then 1,000 to 2,000, that will be our column 3, and less than 1,000, that will be our footing 4. So this would be our footing 1. Whatever is between 2,000 to 3,000, that will be footing 2. Whatever is between 1,000 to 2,000, that will be footing 3. Then less than 1,000, that will be footing 4. So you can group them like that, depending on the FZ, but that is not the only way you can group them, because you've done your technical investigations along along the entire area where your structure is. you can be able to group them depending on the bearing capacity, because this column that is having the maximum, actually it might be having the greatest bearing capacity, and the more the bearing capacity, meaning your soil can withstand load. So your footing will have slightly smaller dimensions compared to a location that has lower bearing capacity, because of course, as we are going to see, whatever loads are applied on the footing have to be distributed onto the soil, has to be distributed onto the soil that is underneath your column. So I'm going to turn off the descriptions. We have seen, at least we know the we have now identified the column that has the maximum FZ. I'm going to apply to turn off. I'm also going to uncheck the FZ, then apply. So this is the column that has the maximum FZ. So another hint would be on beams. The moment you check the maximum bending moment, because beams are meant to resist bending, your beams shouldn't bend. When we are designing beams, we design for the maximum bending moment, so they shouldn't go beyond a certain bending. Now, if at all I choose a beam that has the maximum bending moment, because in the results, you can pull out the beam that has the maximum bending moment as we demonstrated. So if I design for that, then I can go on choosing other beams. As we are going to see here, we are going to design for this column, for this footing, but we shall go on designing other, for example, the edge columns are critical. There are those that we shall design and probably footings cross one another, so we shall adjust them. But for the start, we shall start with this point that has the greatest FZ. So now this is a column, but our emphasis is on the node because we are tackling footings. I'm going to turn off the section shapes. Why I'm turning off the section shapes? I want to extract this node only and leave the column, only the node, because that is where the FZ is. Remember, at first we highlighted from right to left, because when you highlight from right to left, whatever member my selection box touches will be highlighted. But now I want to begin from left to right, because only for example, if I decide to highlight from left to right, whatever is within that box is what will be selected. So I'll highlight from left to right, so I can scroll within my object inspector and you will note that there is a node that has been selected. You can see nodes, there is one out of 55 something thousand. So this node has been selected. When you have the section shapes on, you can still highlight, but I advise you just turn off the section shape so that you can easily identify the node you want to select. So we have the node selected, and so this is still the same procedure. You must be now familiar with it. So I'll just come to my right and just click on provided reinforcement for RC objects. I have this notification because the linked card drawing is not on my side, so it is saved on your side, not my side. You'll get this pop-up. So there are simple cases and manual combinations. You remember the combinations we did, and I think it was Engineer Philip that asked about combinations. So make sure you check manual combinations, because we developed specific combinations depending on the loads we applied. So I'm going to check manual combinations. This pop-up menu is familiar to you, but now this one is tied to spread footings. These ones, you just leave them the way they are. This grouping will be done depending on the stories. You will see as we export whatever stories that you are, a structure. Yeah, you might have a structure that has foundations at different levels. I'm sure you might have seen that. So you might have a foundation at a certain level and another foundation on another. Maybe if we, for example, we assume at 0, we have a certain section of the structure that has its foundations embedded at that level. So maybe the basement. So you might find another level, and you have certain structures or foundations that are embedded at that level. So it will be grouped according to the different stories. Always display this dialog, and these are the different combinations. So the ultimate and the wind in X, Y, and so on. As you realize here, we don't have other conditions, because, for example, for the beams here we had supports, but here we don't have. So we are dealing with foundations. So just click OK. You might not see anything. You shouldn't worry. Just come to story 1 and expand it. You will see the foundation that has been imported or exported. So this is foundation 35, but at this point we can label it. So I'm going to just click once. Just left click. So let us name it. Let us call this footing 1. So when you're done typing, just hit the enter button on your keyboard. So this one is going to be named footing 1. Even in the foundation notes, like the way you saw for the beam notes, column notes, this will be displayed as footing 1. So you'll be able to identify it with ease. By default, if at all the node you've exported is only 1 and they are not 2, by default, robot, this is just by default, it will just attach a footing that is 2 by 2 by 0.6, just by default. So now, this is still the same procedure that we did earlier on. This is a footing, but we need to define properties, just like we did for beams, slabs, columns, so that the software can now design this foundation using those specific properties that we have defined that are specific for foundations. They are right here, so we are going to just go through them, customize them to what we want. Then later on, adjust them here and run the calculation. So it's almost the same procedure like for beams, columns, but now this one is customized to foundations. You must be familiar with these, but they keep updating. For example, item dimensions, what they will update depending on the specific element that we are designing. So we can dive deep. If you remember very well, I think for columns, I don't remember very well whether columns or beams. This one was not active, typical reinforcement. If I'm going to just click, if you adjust here, you only adjust for this specific footing, but it will not apply to other footings. But want to change global settings that will apply to all footings so that now we can just design with ease. So I'm just going to cancel that. So we are going to move through the same. You're familiar with story parameters. So, and now these are story parameters that are for footings. So environment class, we went through this. Story level, you can choose and define at whatever story this is, because you might have foundations at different levels. So I'm just going to leave it. Environment class, cracking, as you are aware or you have seen, there is a small difference between admissible cracking in Eurocode and BS. BS assumes all takes 0.3, Eurocode takes 0.4. And these ones, I'll just leave them the way they are. Concrete creep coefficient, then structure class. We have gone through this. So when you're done, I'll save these as story parameters, Eurocode EN, and this is robot cohort. Yeah, I'm naming it because I have other story parameters, so we can be able to identify it with robot cohort. So, okay, then, okay. As you can see here, it has been updated as, so you can see there are others, but what identifies this that we have set, it is the robot cohort. So, as story parameters are done, we shall move to calculation options. So these calculation options are different for beams, for columns, but these are now specific for foundations, which you will, for example, when you go to the journal, you will see that we are checking for punching shear. But there is still, you can specify a safety factor. And still, the difference here comes in with Eurocode and BS. For BS, you can decide to choose a safety factor, maybe 1.2. But for Eurocode, if the capacity is more than the design force, then it is okay. But for BS, you can choose a safety factor and say maybe 1.2, or a cover, we are going to leave it as 50 millimeters. Concrete, we shall go with C25, and as you can see, it is 20. It is 25 aggregates. Yes, size, as I mentioned earlier on, the size. If I go back to cover, it is not something critical, but it is critical too, because you can't have a cover that is less than your aggregate size. Otherwise, you will not have aggregates between your reinforcement and the formwork face. So longitudinal reinforcement, so I'll just uncheck, but what is now critical is that the longitudinal and the transverse, when it comes to foundations, they are all main reinforcement, because we are going to see you can have bottom 1 and bottom 2 as T16 at 200 in all directions. So they are all critical. So I'll just choose 12, 16, 20, and 25. Okay, 20 and 25. Although for a structure like this, 25 would be so big, but for example, a bridge, a pier base, or an abutment, 25, yeah, usually 20 and 25, 16. But for structure, 25 would be so big. But we shall leave it. So the transverse, I will still choose the 12, 16, 20, and 25. You can choose whatever grade you want, just to make sure it has the strength that you need, depending on the country you're in, the steel grade that you have. I know there are those that are 460, so it should have the grade that you want your steel to achieve. Additional reinforcement, this would be the additional reinforcement that you put on the sides of your footings that have big depth, maybe 0.9, 0.8, 1 meter. You would provide extra reinforcement in the sides to cater for whatever cracking you might have. So we can just choose T12. This is a structure. So save as. So these are calculation options. Eurocode EN robot cohort. We shall be able to identify it. So still, when we adjust, we shall be, as you can see, we have now calculation options that have been customized for foundations. Reinforcement pattern, footing. So we shall have, if you remember very well, in beams we had layer 1, layer 2, layer 3, how reinforcement is organized. The same applies to footings. So I will maintain this because I want the reinforcement to span throughout the footings from one edge to the other, but you can have other different orientations of reinforcement. It might not reach the extreme edges, it might stop either way, but I will maintain this where reinforcement spans from edge to edge. Bus spacing 150, 200, it is okay. So maximum 150. No, let me leave the maximum as 150 would be at 2. So I'll just adjust the maximum to 0.2. Then the pier, this would be the column. But we've already designed columns. What you would only do is to cross-check what reinforcement has robot provided in this pier section. Otherwise, it should be the same like what you have in the lower column at that specific location, not in maybe your story 5 column, because as you know, the loads are moving downward. So the column that is on your story one that is attached to the soil, it's the column that is carrying all the load. So it will have more reinforcement compared to other columns on other stories. Though some designers decide to maintain the same reinforcement throughout, right from story one until just not to confuse people on site. If you have reinforcement that is changing on every story, yeah, it is okay, it can change if the contractor can maintain it. If you're not sure about the contractor, then you can maintain the same reinforcement from story one up to story two, though it would be, you would have over-designed. But yeah, there are those practices in field. The door bars, the door bars, these they're like the starter bars, so you can be able to define the L, the length by which they are going to put root out. You can be able to define all these, but we don't have to. We have our columns designed, and that is the reinforcement that we shall take. So the connection to the column, it is set to auto, and the shapes. These are the main rebar. The main rebar, so I'm going to just give it hooks on either sides. You can just change to whatever you want, whatever hooks that you want, but these are going to, the way this one is, it is going to span from this side to the other side. So I've just given it hooks at 90 degrees. When you're contented with what you've adjusted, all these can be adjusted if you want, but we are going to maintain the same bars from the columns. Those are the same bars that will go, that will act as starter bars. So I'm going to just save as, and reinforcement pattern in robot cohort. Okay. This has been adjusted. All right, so now let us go to, okay, we've adjusted reinforcement pattern. These ones, item dimensions, you're familiar that it's these ones that are open here. So for example, when we go to the journal, this shows the foundation type. So you can have this, you can have the strip and the different dimensions. As I said, by default, it comes with a 2 by 2 by 0.6, what is displayed here. This column is automatically captured from the model. It should be similar to the column that is attached. There is eccentricity, so you can be able to shift your column at whatever position you want, depending on the constraints you have on site. Usually for corner columns, you might have a nearby structure and you can't exactly position it in the middle of your footing. So you'll be forced to adjust the eccentricity in X and Y in order to position the column the way you want it to be placed. So the geometry type, we can have this, or you can have this where you probably, so I'll just click on this and apply. You will see this adjusts into, this probably where you have cases of punching shear and you're not so certain, so you can have these edges to add extra punching. So this is for the combined footings. We shall see it. It will only be active when we have two columns that are coming in to be designed as combined footing. So I will just leave it to this and apply so that it adjusts back to. And this is the eccentricity I was talking about. So you can be able to change the eccentricity in Y and X and position the column the way you have it on site, depending on the constraints that you have. The pier, yeah, this is door weld, so it will have reinforcement like this. There's also this, you can still use them in adjusting your column, but we shall just leave them the way they are. There's nothing to change. Load definition. Engineer Philip mentioned about a tank that is on top of maybe the last floor or the top floor. So we can still have extra loads that are not captured in the structure that probably would influence this footing. So we might have a water tank maybe some few meters away from where the footing is, and it is probably resting on ground. It is not anywhere attached to the structure, but the weight or the loads from it might influence the foundation. So you can be able to add extra loads, point loads, moments, all these, you can be able to add extra loads if there are any extra loads onto this footing that are not captured in the structure. So you could add them from here. Sorry about that. I think you lost me for some few seconds. So I will just share my screen again. I think I have to. So you can just type a one in the chat box to confirm that you can see my screen. I don't know, I had a small, all right. So my screen is visible. I don't know what that was. So I'm going to just close this. I don't know where it happened, at what point, but I will check the cell definition. So I was saying by the time you go into design, geotechnical investigation would have been done to the project site. So you understand or you have extensive knowledge on the soil that is beneath the site that you are dealing with. So in the soils, this is when we get to define the soil that is beneath. So I'll leave this as 0, 0. So the foundation is going to be probably, if you have soils still that probably you're going to cut and spoil to a certain depth. So meaning your foundations will be at a depth that is way greater than what you have on site. For example, I would just assume 1.5. So you would capture it here, but I'll just leave it as 0. So I'm assuming where it is, that is where the foundation is going to, but you can be able to have these foundations at whatever level that is firm. The pi level, this one, I'm also going to leave it like this. Then the minimum difference level, I'm going to leave it as 0.5. And now what is most important is that you can define a water level. So you can define the maximum and minimum. And of course, this has effects on your bearing capacity, on the pressures that will be underneath. So if you have, I know, you find cities that are in wetlands. So the moment they tell you to design a structure of a certain site, when people go on site, all they encounter after excavating 0.3 meters down, there is water oozing out. So yeah, you can be able to define the water level at which it is, and the software will understand its interaction. It will have a better interaction of the site. The soil, this is where the database is. So robot is, because you have the geotechnical report, so you know the different layers that are underneath. And still, depending on the structure that you're designing, some normal structures, they just dig a trio pit and go and do a DCP at maybe a certain depth. Some other structures that are critical, like bridges, designers go and bore and do bore holes at whatever depth, 20, 50 meters, and the entire soil profile will be highlighted very well, that on top you have a soil that is of this bearing capacity, it runs, it is this thick, then there is another soil type of this bearing capacity, of this angle of friction, then at this depth, at 20 meters, maybe at 30 meters, you have a bedrock that is of this depth. So you have all that within your geotechnical report. So let us take an assumption that the first layer is gravel, and at 2 meters or at 1.5, there is sanded gravel. So I'm going to take at 1.8, there is sanded gravel. You can be able to give these different colors. And you can see so you can populate this with the entire soil profile as per the geotechnical report, because you have the geotechnical report. So the software will now understand that the footing is seated at this depth, and within that depth, there is a soil of this bearing capacity, and so on and so on at this depth. So the software will understand fully what you're dealing with. After adjusting this to match the geotechnical investigation that was done according to the report you have, so we can call this soil soils or soil parameters, Eurocode robot cohort. Okay, and then close. So I think we didn't, sorry about that. I think we didn't. So I'll save as. Okay, apply, then close. So you can see it has been updated here. The last one is the geotechnical options. So in the geotechnical options, literally it is going to do, for example, it will verify for rotation, it will verify for sliding, it will check limits of settlement. But now what is critical, one, have this checked so that it checks for rotation, have this checked so that it verifies sliding. But now sliding with soil pressure considered, this is not a retaining wall. I don't expect it to slide, so I'll just check none. A limit, so settlement still, depending on the structures you have and the geotechnical investigations that were done, I will, for example, I'll just give an example. Still on highway projects, for example, if you are to install a box culvert in a swamp, they will do a borehole there and they will extract out whatever material is there. If at all it is clay, they will go and cut out settlement. So they will be able to tell that this clay, when loaded, it will have this settlement. So you'll be able to tell whatever settlement you have depending on the different soils you have. But you can limit it and say, let it settle by 5 centimeters. So, so if at all we quote a smaller value of settlement, meaning your footing should be able to resist that, should not settle beyond that, you might end up with bigger reinforcement. But still, if you specify bigger settlement, then your structure will extensively settle, and then you might end up introducing other secondary stresses within your structure. Stresses, there's calculation method, semi-empirical, but now what is important is that you have the geotechnical report and you know the allowable bearing capacity. So we can quote our bearing capacity. I don't remember what it is, but I'll take 250 kilonewtons per millimeter squared. I know Engineer Gatimos specified it in the, I'll just take 250. You have it in your, you don't have to worry because you have it within the geotechnical report. So they will tell you the bearing capacity the soil can withstand, the soil that you have under your foundation. Design approaches, yeah, there are design approaches 1, 2, and 3. So robot incorporates these 3 design approaches, and basically they are they guide on the application of the partial safety factors to ensure reliable verification of the ultimate limit state for your foundations. For example, the A1, that is for the permanent loads. The M is for materials, the R is for resistance, meaning the software is going to specify different partial safety factors in these three design approaches. For example, the most common one is the design approach one, because it's the most comprehensive approach. It has two separate combinations that are checked. As you can see, these ones have 1-1. As I said, A is for the permanent actions. For example, now if the software assumes, for example, the first combination, this to be 1.35, for combination one, this design approach one, the partial factors are mainly applied on the action. So it is going to only vary the action. So we can have the permanent actions are varying from the 1.35 and the variable at 1.5 as they are stated in the combinations. Then it will bring in the materials. So as I said, design approach one is basically varying the partial safety factors for action. So it will keep the materials as 1.0 and it will keep the resistance as 1.0. So it will just go on varying. The A2 now will vary, it will keep the vary the M2 and the resistance. But these ones are typically 1.0, 1.0. So if at all you to choose design approach 2, now this one, the design approach 2 shifts now the variation onto the materials. So it will, for example, take materials as to have a partial safety factor of 1.25, and now it will keep the resistance as 1.0 and so on. The same applies to design approach 3. This applies partial factors to actions between, but it differentiates or it distinguishes the structure and the geotechnical factors. So if it applies a 1.35, then that will be probably on the structure, then it will apply another factor on the geotechnical actions. But the most common one is this one because it has two combinations. So I'll just leave it, it's just an explanation, but you just leave it in design approach one. So when you're done, you save as these are geotechnical options, EN, robot cohort. Okay, then as you can see, they have all been updated and the calculation is incomplete. So now when you're done, so you've done the biggest part of, as you know, when we're designing all the procedures you have seen for beams, columns, when you finish with these ones now, the rest are just iterations. So one, make sure you're in the foundation view. These ones, we are going to see them later on. But because when you're in the foundation view, that is when you have this calculator active. If by any chance you're in the structure, you have this other calculator active, and they, as we have seen, they all do different. So make sure you're in the foundation view and hit calculate. just leave these ones. We are not doing a design review as we saw for beams. You can just generate drawing or keep the existing reinforcement, but this is something new. So just hit the calculate. It is going to calculate. As you can see, the footing is checked, footing 1, and it has specified a square footing of 4.5 by 4.5 by 0.7. Now let us dive deep into what it has done. So when you come to the foundation results, you remember that 0.25 that we specified, your pressure should never exceed that. So you can see this is 176, that is way less than the 250, and it is the same at all edges. Why is it checking all edges? You remember the differential settlement that we talked about. If you analyze and you realize probably the sides of the footing have different pressures, then it means the soil that is on a side that has more pressure will experience more stresses compared to the soil that is on the other side that has less pressure. So if the soil experiences more pressure on one side compared to the other, it might deform. So when it deforms, you will have differential settlement at that specific location. But it's not a must that you have them equal at all corners, but that difference should not be so big, because if you have more pressure on this side, then the soil on this other side will experience more stresses, more pressure compared to the soil on this other side. But good enough, it is way below the bearing capacity of the soil, so we don't expect the soil to deform. It will take the loads, so we don't need to worry about that. Come here down to capacity. As you can see, it checks the capacity against the ultimate limit state. The contact pressure, these are all ultimate limit states, but average settlement, it checks it against the serviceability limit state. And the same applies to the settlement. It checks it using the serviceability limit state. I hope you're aware that sizing is done using the serviceability limit state, but the reinforcement is applied using the ultimate limit state. So these are the foundation results. Then foundation reinforcement. This is it. You remember there is a shape, there is a pattern that we specified, and we said that the reinforcement just go from one edge to the other. So this is it. If you just specified maybe the other one where reinforcement comes and does not reach this edge, you will still see it in this. It is still okay, depending on what you're designing. And as you can see, I'll just hold down the shift button and the zoom button on my keyboard and rotate this. So as you can see, this is a footing that is singly reinforced because it has reinforcement on the bottom side only. There is no top reinforcement. So all the reinforcement is summarized here in the journal, but there is also detail that captures the entire reinforcement that is within the footing. You can just select any and it will highlight in the model. You can see these it is providing a T, so I'll just check this just to. So these are T12. This is for the pair. This one should not give you any headache. You have your column design, so you shouldn't worry about it. So you can see it has it has provided T16 and they are 52 in number. But now we are going to interrogate this further. You shouldn't worry. So I'm going to move to the foundation notes, like the way you saw beam notes or column notes. So it summarizes what you've gone through, the geometry, the assumptions, the material, the loads. It goes through the different load combinations, the ultimate, the geotechnical. You remember the design approach I was mentioning. So these are the different design approach one, and these are the different partial factors. So it varies. The design approach, as I said, they vary the partial safety factors. Soil, the soil that we defined. These ones you just get from your geotechnical report. So it will go through the limit states, the ultimate, and it will check the uplift sliding, average settlement. As we noted, these are serviceability limit states. It will check rotation. Then it will design, it will check, of course, punching shear. The column shouldn't punch through your footing. So it will check your foundation, your footing against punching. What is now important is the required reinforcement. Required and provided, we saw the difference. So you can see in the X, this is the reinforcement, the area of steel that is required. And in the Y, this is the reinforcement area that is required. The top, this is bottom, the top, you can see there is none, and that is why it is singly reinforced. So it provided T16, there were 52, but now we can go further and check. I'm going to just open my chart. So 1148, let us just confirm what 1148 would give us. So 1148, I can decide to provide 1148. This is 1149. So I can decide to provide a T16 at 175 that gives you 1149, or I can provide T16 at 150 that gives me 1341. It's your choice as the engineer. It is your choice as the designer, so you can choose. Now, what is most interesting is that most softwares, when you design, you don't have a view of the interaction of the footing you have designed and the structure, but that is not the case with the robot. As you can see, this is the footing that we designed, and it is automatically updated in your model. So this gives you an understanding of the influence of this footing on other footings that you're going to design. So you're able to see it in the model. Now let us do something interesting. We can turn it into a combined footing, or let us leave it and design something else as a combined footing, then we shall. So to design a combined footing, or I can, let me just choose something else. Let me design these two, this one and this one, as a combined footing. But you can design one by one, then you see how they are interacting. When you see them are crossing one another, then you adjust them into a combined footing. So to do this the easiest way, I'm going to repeat the process. So these ones, this is what we have designed, but let me design this and this as a combined footing. So as the procedure is, but this one now is going to be much faster, and because we have all parameters set. As I said, our interest is in this node, and we can extract it. So I'm going to just highlight from left to right, and you can see there is a node that is selected. But because I want to design these two as a combined footing, so I'm going to hold down the control on my keyboard, then select this other node, still the same way, left to right. And you can see there are two nodes that are highlighted. I'm going to just go to provided reinforcement so that I export the two nodes. We maintain these as manual combinations, then okay. The moment you highlight two columns, if you remember very well, we never had this notification. We never had this notification earlier on. This notification only pops up when you have two nodes highlighted. So I was saying you only have this pop-up when you select two columns. So the software will hint you, do you want to the software will provide a hint that do you want to design one spread footing with two columns, just say yes, then it will export the two. So as you can see, we are in story one. When you don't see anything, just come to story one and click on this. So one, let me just click in space. So I'm going to just click again. Left clicking, so I'm going to name this combined footing one. Let this be our combined footing one. After naming it, I'll just hit the enter key on my keyboard. So robot will export. These are the two columns that we have exported, and this is just a start footing. This is just for the start, just the normal dimensions it is proposing, though not yet designed. So as we also, this is where it becomes interesting. All I have to do is come to the story parameters and look for what. So it's this one, robot cohort. So I'll also go to soil definition. Why not if you don't have other, probably the more you work with the software, you have to develop other parameters that are specifically tied to that specific structure that you're working on, and they will all be embedded within the software. So when you're done, let us just maintain these the way they are. We are going to adjust them later on after designing, when we probably find that what we have designed does not display what we want, so we shall adjust it from here. But for now, all these have been set to the parameters we set for foundation, so I'll just hit the calculate. Note, make sure you're in foundation view. When you're in structure, you have something else. So I'll just hit the calculate, and then problems with reinforcement arrangement. This is not big. We shall see how to maneuver over it, because in the foundation notes, they're going to give us the area that is required in the different directions, X and Y, or bottom and top. So we shall be able to decide that we are applying this reinforcement at this spacing in a given direction. So this shouldn't be an issue. As you can see, it is a square. This is not a square, it is a rectangle 6 by 5.5. But now what is important is to go back to the structure and see what we have, what we are proposing. So I was saying, now it has designed, this is the combined footing, as you can see. So, but we can further adjust it into a rectangle. This is very big, 6 by 5.5. We can adjust it. Now, how do we adjust it? I'm going to go back to the foundation. So as you can see, it has A of 6 and a B of 5.5. So let us let us increase this to, I want to reduce it. Let me increase this to 6.5 and then reduce this to 4.8. But now when I reduce this, it's just a check. I'm going to fix them so that I'm telling robot you can adjust other things, but leave these 6.5 and 4.8 the way they are. You can adjust the thickness and so on. So I'm going to apply so that it updates to this. Then I'm going to hit the calculate so that now it checks whatever I've specified, whether it meets. As you can see, punching and all this reinforcement in X has not passed. So we are going to go back to the structure, but let me leave it at 4.8. So I've increased it to 7. I hope it will work out. So I'm going to hit the calculate again. As you can see, this one is okay, but now let us go back to the structure and we see what we have adjusted. How is it interacting? I think the 7 is too big. Okay, we can, to have a better understanding, we can first design one footing, these ones, because they are isolated, they're one by one, and we see their interaction with this, then we can adjust this to meet what we want. So I'm going to just go back, although I can select it from the structure. So I'm just going back to just repeat the same procedure over and over again, just to have a better understanding. So I'm going to pick this. How do you pick it? From left to right, and so I will repeat that from left to right. Make sure you have the node selected. It's not selected, otherwise it would highlight here. So I'm going to select it again. Left to right, and one node has been selected, then I will I will pull it into the design template for foundations, manual combinations, just click OK. I will apply okay, for some reasons it has gone into, okay, it has gone into story 2. It is okay. Let us just change this into what we set. I'll just look for anything that has robot cohort because that is what we set. Then I'm done. I'll just hit the calculate. I've unchecked this so that the software now can vary it. As you can see, it has, this looks to be very big, a 5.3 and a 2.5. I think it took, this is what I was explaining, that the pressure has to be, it shouldn't, this one is, we are going to adjust this. So I'm going to go back to its foundation. I think it picked two, for some reasons, I don't know, I'm going to, it picked two columns. Let me just go back. Let me do it from here. I'm going to, let me do it from here. So I'm going to, okay, let me go back to the geometry then. Yeah, this is it. So I'm going to pick it from here. Just be patient with your cursor and make sure you just check the object inspector and ensure you have one node selected. I mean, combinations, yes. So I'm going to just extract this. Combinations, okay. Then it's right here. So I'm going to turn this, choose anything that has robot cohort. Robot cohort. Okay, then hit the calculate. Okay, so it is proposing a 2.3 by 2.3. Let us check how, you can see the soil pressure 0.2. So these ones are cross. It is not like what we had earlier on, 0.2, 0.19, 0.19. And they are all less than the bearing capacity of 250. So I'll go to the foundation. Still, this is single reinforced and they are all T12. They are 30 in number, but we can now go to the foundation notes and go to, I've gone through this, so that is why I'm just scrolling down and I'm going to, my interest is in the area of steel. So the top has none and the bottom, this in the Y, 659 millimeters squared per meter, and in the X7, 82.7 millimeters squared per meter. Let us take the 782 and we apply it in both the X and Y because it is greater than what is in the Y. So I'm going to just go back to the reinforcement tables. Okay, it skipped my head, 782, all right. So I'm going to 782. So 782, we can have T12 at 125. That will be 905. Or 890. It was 9 what? I'll pick it again. 782. Okay, 782. 782, I can decide, I can have T12 at 125, but 125 is close, so that it gives me 905 versus 782. Or I can take it to the extreme. I provide T16 at 250, which gives me 804 versus 782. Okay. Yeah. So you can provide T16 or T12. Robert specified T12. I guess this is at they are 30 in number. Let us go back to the structure and we see its interaction with here. They are not, as you can see, they are not touching one another. Let us check out very first the corner, these corner columns. They are critical, but you saw how we change the combined footing into a rectangle, a square, by just adjusting those different parameters. You fix them and then you just please take note when we are modeling. As you can see, I think engineer moved the column and left the node. Remember when we were modeling, we said if you're to move something, if you're to move a column, make sure you select it and everything that it has. So this is a sign that this column was moved, but the node was not moved. That is why it is still attached at that location. So I'm going to just pull out this. So same procedure, but now much faster. So I'm going to pull out the corner columns. Let me pull out this. Let me pull out those ones that don't have issues. Okay, so I'm going same procedure from left to right. Let me as well try out something else. So I'm going to bring in that. I will bring in this. 3 nodes have been selected, then provided reinforcement for RSA objects. Manual combinations, okay. Level 1, I hope there are these ones. Let me just call it 14.2. Then hit enter. So same procedure, but now it is faster. We've already set the robot cohort foundation design parameters. All I have to do is apply them to those and hit calculate. Okay, the arrangement shouldn't worry you. We are going to, so these are 1.8 by 1.8 by 0.3. We can check out the soil pressures, always check them out. And the reinforcement, they are still T12. So in the X and Y, these are bottom, so it is single reinforced. We can check out the foundation notes. As you can see, this is footing 2. So when you change it here, it will update in your foundation note. We've gone through this. I'm just going to, but now note we've gone through this, but let me just go to the area of steel. So 685, yeah, and so we can apply 685 in both X and Y. Still, we can check it out, 685. Let us go with treatment of 685. We can apply, please choose a spacing that can easily be measured with a tape. Increments of 50 is okay. 175, someone has now to note that these other 5 extra millimeters. So you provide spacing that can easily be, so we can provide T12 at 150, that gives us 754 millimeters. So I'll go back to, it is single reinforced. So we can go back to the structure and check it out. So this is it. These are, remember when I was selecting, I selected 3 of them at once. So they have all been updated in the model. So everything you design gets updated in the model automatically. So you have a better understanding of the interaction of the different. The moment you design one and they are meeting one another, please turn them into a combined footing. You saw how you can delete it, then select 2 columns at once, and then you turn them into a combined footing. Let me design this just as the last one. I think there is engineer, engineer Cyprian. I shared something in the chat. If you don't mind, you could have a look at it. And I think it was because I see it has the different layers, the different liquid limit, the plastic limit, the PI, and so on for the different layers. So yeah, all this information will be available in your geotechnical report. You shouldn't worry, you just need to know what to pick and where to pick it. So I'm going to, let me just use the remaining few minutes to, so I'm just repeating what we did. So just to reinforce what we've done. Please always check the object inspector after selecting, and you should have if your intention was to select two nodes to turn them into combined footing, then you should have two nodes selected. You have a node selected, just come to the same procedure repeated over and over again so that it becomes part of your manual combinations. Okay, and then it will be exported into the foundation design. Name it, maybe this is footing 3. I'll just name it F3 to denote footing 3. Hit the enter key on your keyboard. Change this to what you set earlier on. This will vary depending on the structure you're working on. So when you're done, just hit the kite weight. Before you hit the kite weight, make sure you're in the foundation view, otherwise you will hit on a different calculator. This is a 4.1 by 4.1, so we can visualize its results. As you can see, the pressures don't differ much. It is single reinforced. And the area of steel, this is in the Y you need, in the Y you need 1146, and in the X you need 10. So we can look for the 1146 and we provide that. As you can see, it has provided T16 at 45. It has provided T16 and they are 45 in number, but you can be able to choose whatever steel you want and how it will be arranged. You have that. It is easy to be economical. The software will not, so you have to choose the reinforcement you need. It's a pleasure that at least we've had a session minus any internet issues or so. It's a pleasure. I think we were 30 plus, but yeah, towards the end we are 27. We shall share a video, a small short tutorial in regard to raft foundations. They are designed more like slabs. They are designed more like the slabs that Engineer Gatimo designed with you. So it will be literally the same procedure, but we just have to, for example, if I wanted to turn this into a raft, I'll have to remove these supports and then draw a slab at that specific level. But when I'm drawing that slab, I will bring in, let me just go back to the geometry so that I leave this. So when I'm drawing that slab, I'll bring in this parameter of foundation elasticity. If it is homogeneous, yeah, I'll bring in this parameter. This is where this parameter comes in. So when I attach it to the foundation, the software will be able to identify that the slab I've attached has properties of foundation elasticity. And still within these properties, there is the geotechnical information that you have to adjust as we've done so that it meets the soil, different soil layers that are beneath this slab. So the software now will understand that you're not only bringing in a slab, but you're bringing in a slab that is in contact with soil. But we shall share a small recording because you might want to have probably a raft foundation at one point. So we shall just share a small recording on that. But it will just be a repetition of what Engineer Gatimo did earlier on in slabs, because it will be designed as a slab, but with this soil foundation elasticity. And still, when you're analyzing results, you will be able to view now the soil reaction underneath this slab. Otherwise, allow me stop here. Allow me stop here. It's been a pleasure having you and sticking with us. This is Road Sub, where we get to learn and grow together as fellow engineers throughout the world. So it's a pleasure to have you, and I don't have any questions in the chat box, so I will end it here. But if you don't mind, look at what engineers Priyan shared. That is part of foundation. So allow me to stop here. I'll stop sharing my screen. It's been a pleasure, and have a good night. Okay, I will stop the recording. Have a good night. Please, tomorrow we have a session. Engineer Gatimo is going to demonstrate a few concepts regarding the different questions you asked, exporting the model into Revit. We also have our Revit cohort that has just started. We had a technical information session yesterday. So we are just, we have a new cohort of Revit. If you've done design, you might want to know your design should not remain on your laptop. It has to be read by people on site. So let me not take much of your time. Have a good night.